We're going to talk about random variables, continue, but this time we're going to talk about the continuous ones. So all random variables, actually, whether continuous or discrete, can be described by either their PDF or their CDF. The PDF is the probability density function. That's the probability of a particular outcome, or range of outcomes. For a continuous random variable, that probability of any single outcome is infinitesimally small, so we might look over an interval. The CDF is the cumulative distribution function, the probability of an outcome that is at least as big as some particular value. With a PDF, we calculate something like what is the probability the random variable x will be between values a and b. In the continuous case, we'd have to integrate, while in the discrete case, we'd just take the sum. You should remember this from calculus. Instead of a sigma to show the summation, we use that squiggly s thing, the integral sign. The CDF, the cumulative distribution function, provides the probability that some observation from x will be less than or equal to some value b, which is the integral up to b of that density function, the PDF. So one of the most common continuous random variables is the normal distribution, which has that classic bell shape that I've shown there. That's the PDF for the normal, while the CDF for the normal is that kind of S-shaped thing there. And that classic bell shape of the normal distribution is probably what you're most accustomed to seeing. The normal distribution is called normal because it's common, ordinary. See it all the time. It pops out in all sorts of different circumstances. Many statistics have a distribution that tends toward the normal distribution. We talked previously about the binomial distribution, which converges towards the normal, but a lot of others do, pretty much the same way. The average of statistics, such as the mean, will usually have a normal distribution. We denote that as n mu sigma, where mu is the typical representation of the mean, and sigma represents the standard deviation. Just a little flag on the notation. Sometimes people will use the n mu sigma squared, the variance, instead of the standard deviation. Just got to be on the lookout. If somebody writes n, say 0.16, then the second term could be the standard deviation or it could be the variance. Anyway, here's a nice example of PDFs from a paper by Jim Hansen on temperature anomalies in the northern hemisphere over land in different decades. It's a nice illustration of how there's been a rightward shift of the whole distribution, and actually those do look pretty normal. You can see that relative to the earlier years, the 80s and the 90s, the first decades of the 2000s, had increases in the number of positive temperature abnormalities. So one of the things that makes the normal distribution actually kind of special, but because it's special, we see it more often and therefore it's more common, i.e. normal, is that if we have a linear function of a normal variable, then that linear function is itself going to be normally distributed. If x is normally distributed, then y, defined as a plus bx, is going to be normal as well. This is not universal for other distributions, just the class of Levy distributions. Having linear functions of normal distributions being themselves normal is awfully convenient, and a big part of the reason why normals are so common, i.e. normal. Linear functions don't break the normal distribution property. So we often standardize normal variables to form other statistics. Now, despite the terminology and what you might hope, standardized does not quite have a, standard meaning. Version 1 of standardized, which is more common in mathematical theory, is subtract the mean divided by the standard deviation, get something usually called z, with z equal to x minus x bar, that's the average, divided by the standard error. Z would have a mean of 0 and a standard deviation of 1. But it could have some pretty large values, both positive and negative. Another meaning of standardization, I call version 2, is more common in machine learning algorithms. That version would scale everything to a unit interval, so all the observations can be squashed between 0 and 1. That is again a linear transformation. We define w to take every value of x, subtract off the minimum, divide by the difference between the max and the min. So both z and w are going to have a normal distribution as long as the underlying x's have a normal distribution. But so anyway, how normal is the normal? Really, we're calling it that, but is it really normal? Later, when we talk about hypothesis testing, we'll pose the question, how big is big? Here we pose the question, how normal is normal? We ask the big questions here in this class. So I've shown in a simple experiment here using census data. There are in total nearly 200,000 people. The average wage is about $38,000 a year. But the standard deviation is huge because quite a lot of people reported zero wage. They're not working. Maybe they're old, maybe they're in school or doing other things. They're not in the labor force. So that histogram shows the distribution of wages where we can see that far and away the modal outcome is a zero wage. Then some people have pretty big salary. So it would seem a hard test to the assertion that the mean is going to have a normal distribution even though the underlying data is really quite non-normal. But you can see that it does. I formed little polls sampling 100 people out of that 200,000 group. I calculate the average within that little tiny poll of 100 people, and I plot those in the black bars down at the bottom. Now you can see that, yes, somewhere a little above 30,000 is actually a pretty common outcome, even with just 100 people. Out of those 100 people, typically 60-something have zero values, so it's really just averaging a whole bunch of zeros with only about 40-something that are not zero. But look closely at the vertical axis there, and there are some that are over 70,000. That's a bad miss, but there are others that are really genuinely pretty close, which I think is kind of cool that it works that well. So on the left is a histogram of the average of this 100-person polls. Most common outcome you can see is somewhere a little bigger than 30,000, so pretty accurate. There's some fraction of polls that give wacko values, total extremes, but overall, it's a pretty good distribution. Next step is to ask, well, why 100 in the poll? What if I had a different number of observations? Okay, do it for samples of size 10, 50, 1,000, 10,000. That's that other picture on the right. On the horizontal axis, I have the base 10 log number of observations in the sample. So it starts in the x-axis labeled 1, which in logs means 10 to the first power. That's 10 observations. 2 is 100 observations, 3 is 1,000, 4 is 10,000, etc. You can sort of see the sprawl of different values in these. If I only pick samples of 10 people, then I get outcomes between 0 and over 100,000. So 10 people is a very rough estimate. But you can still see there's a certain amount of bunching around the true mean near 30,000. Then we go to 50 or 75 observations in each, and by the time we're at 100, I've really scrunched down the amount of variation. It's even more scrunched down by the time we have 1,000 in the sample, much, much smaller with 10,000. Squeezed really tight. Maybe it looks like a funnel with a smaller and smaller range of outcomes as we use bigger sample size. You can see there's definitely an increase in accuracy as I increase the sample. Now, hopefully your econ brain is also thinking about this saying, well, that looks like diminishing marginal returns. Going from 10 to 100 brings a huge increase in accuracy. Going from 100 to 1,000 brings a still noticeable but much smaller increase in accuracy. Going from 1,000 to 10,000 is an even smaller increase in accuracy. For anybody who works in the polling business, that's one of the key insights. There are diminishing marginal returns as your poll sample size gets larger and larger. Later, we'll talk about some of the implications of that. But so we often want to calculate areas under the normal distribution. It's a basic aptitude in stats. I'm going to ask you to do that on the exam. The standard normal, using version 1 of standardize, has mean 0 and standard deviation 1. It's symmetric around 0. Total area under the curve, that bell shape, is 1. We often want to find the areas of segments of that curve. The key part of the calculation is using the symmetry of the normal distribution. When you look at the value, commonly you'll get an answer something like, what is the area to the left of minus 1? That's there on the left graph. But what if you actually want to know the area in both tails farther from the mean than either minus 1 or plus 1? How do you calculate that? Well, since I know the area to the left of minus 1, then the fact that normal distribution is symmetric means that the area is the same as the area to the right of plus 1. So the area in both tails is the sum of those two areas. If I do know just the area of that piece on the left-hand side, I can figure out the areas of those other pieces with just a little bit of arithmetic. Doing these calculations in R is either going to use p-norm or q-norm. You can look at the help function for that. It's pretty straightforward. If you need to find areas on a normal, you can Google, you can ask Siri or Alexa or whatever your favorite sage. You can even do it in Excel. I'm not going to get into details for now, but I think lecture notes have some good instructions on that. The normal distribution is surprisingly common. That's why it's called normal. Even though there are aspects of it that are genuinely kind of weird, but we call